Okay, so today we're going to talk about exponent rules, simplifying radicals, just sort of some mechanics that we're going to run across. We'll look at some examples. I've got the worksheet here. We'll work through some of those together. Take some time. We have here the exponent rules. So with these, you've seen all these at some point. A lot of times you don't consider them for rational exponents. That's really kind of the thing we want to make sure we're good with. We get a lot of rational exponents in calculus. Like we tend to never use roots if we can help it eventually, and we just use rational exponents instead. It's a lot easier to use a 1/2 power than it is to deal with the square root. We're going to find out. So to kind of summarize here the different properties, we have a base to the m power times the same base to the nth power. Right? So base times the same base, you add the exponents. Base divided by the same base, you subtract the exponents. A base to the negative m power is 1 over the base to the nth power. Now there's some other ways around that one too, like we can talk about that. But anytime you have a negative exponent, you can move that base from numerator to denominator, or vice versa. It'll change the sign of the exponent. So a lot of times simplifying, I just get rid of all the negative exponents right away. Kind of deal with that. And then later, once we start doing some calculus techniques, we'll want to get negative exponents because they're still pretty easy to work with in terms of that. Here is if you have a product to a power, you take each factor to that power. Same thing for a quotient. Now notice if it's a plus b, there's no rule for that up here. Then you have to actually multiply it out, do the work. If you have a base to a power raised to another power, that's where you multiply the exponents. And then we want to be able to convert between radical notation and rational exponent notation. So again, that's radical, RAD, right? And rational, RATI, rational. But if you have an mth root of some base, that's like taking it to the 1 over m power. A lot of times, though, you'll have a power like n over m. Maybe it's a 2/3 power or a 4/5 power. And this is as long as it's reduced. It's the same as doing the nth power of the base, that's from the numerator, and then the mth root of the number. And this just shows us you can do the power first, then you can do the root, or you can do the root first, then you can do the power. In general, if you're able to do the root first, you want to. It makes it a lot easier. An example of that is, say that you are asked to evaluate by hand, the cube root of 64 squared. Now, I don't want to square 64. That seems like a lot of work. And plus, I'm going to get a giant number that I don't know. I'm not going to know the cube root of it either. So what we want to do here is take advantage of this fact that we can go ahead and do the cube root of 64 first and then square it. Well, we know the cube root of 64 is just 4, and then the answer would just be 16, opposed to the other way, which would have been a lot of work, right? And its cube root is 64, it's 4 because 4 times 4 times 4 is 64. So some examples from our worksheet here. I just put 3, 8, and 10 up here. Let's just kind of work through these and make sure we're able to apply these rules, kind of see how we can simplify them. A lot of times, the simplifying is not that bad, but there might be different forms that we just want to recognize that the answer could look this way, could look a second way, and they're completely the same. They can mean the same thing. So for number 3, we have 10 to the 5/2 divided by 10 to the 3/4. So that's an instance of the rule where we have a base divided by the same base. We're going to subtract the exponents. So 10 to the 5/2 minus 3/4. Right, we're going to subtract the exponents. We need a common denominator. So that would be 10 over 4 minus 3 over 4. So 10 to the 7/4. Now on this one, I would stop here because it started off with rational exponents. We probably want to finish with rational exponents, would be a reasonable way to do it. But there are some equivalent forms that we should be aware of here. So again, the 7 means the 7th power of 10, which is what, 10 million, I think? A 1 and 7 zeros. And this means the 4th root of 10. So, if you might see this written as, the 4th root of 10 to the 7th. That would be equivalent. Okay. Now, if you wrote it like that, though, you could also simplify it, and well, you could say that this is the 4th root of 10 to the 4th times the 4th root of 10 cubed. Right? We just broke it up because we know that 4 plus 3 is 7, so we can break the powers up. Well, the 4th root of a 4th power, they just cancel each other out, correct? So that would just become 10, and you could say the 4th root of maybe 1,000, or the 4th root of 10 to the 3rd. That would be a way that you might see it written also. It's just to be, this might be better in a lot of cases, and this might be better in other cases. It just depends. Right? We just need to know that they are equivalent, especially when you're checking solutions and things. Here's 8. I thought had some interesting features to it. Up top, we see 4 to the 3 halves times 4 to the 15 fourths. So we know we're going to add these together, the exponents together, right, to get that power. The bottom here is 4 squared. Well, it's 2 squared, and 2 squared is just 4, right? So we should probably take advantage of that. Or I thought maybe even a better way would be to replace these with 2 squared and kind of go from there just to see how simple we can get this thing. Just because 2 is a prime number, 4 is composite, so I think 2 is probably the winner there. So let's rewrite this top 4. So let's write it as 2 squared to the 3 halves. And then we'll say 2 squared to the 15 fourths over 2 squared. Let's see what we get here. Now, we can multiply these exponents, correct? We just get 2 cubed. Here we multiply, we get 2 to the 15 halves over 2 squared. Are we doing okay so far? Now you're going to do 3 plus 15 halves minus 2 is what we're going to do. Now I'm kind of looking here. These, that would give us, if we cancel that, we get 2 times 2 to the 15 halves, which is 2 to the 2 halves times 2 to the 15 halves, which is 2 to the 17 halves, would be how that could simplify. Would be one way to do that. I guess if you wanted to have it in terms of 4s, you could. Now this is pretty weird, right? It's the 17th power of 2 square rooted, but it's just a number. Right? So we could do that. Any questions with that? Yeah.
Would we be allowed to leave those 4?
Great question here with this is we had 2 to the 17 halves. What would that look like if we'd left it as a 4? Right? So we could go back and do it all with the 4s, but I don't have that much energy right now. But we know that we can replace 4 to the 1/2 power is the same as 2, right? So we can replace 2 with the square root of 4. And then we can multiply these powers, and we get 4 to the 17 fourths. But again, it's not quite as good because 2 is a composite, or 4 is a composite number. 2 is a prime number. It makes it look a little bit nicer. But yeah, it could look that way. There's lots of ways. I don't think it's really worth it to do again, there's lots of ways you could write this. You could even do, no, I don't need to do that. All right, so number 10 here should be, like here with this one, we got to be careful. Here's 8x to the 1/2 to the 2/3. Some things to watch for here. This 1/2 is only on the x. Okay, so x to the 1/2 will get raised to the 2/3 power, so we'll multiply those exponents. But don't forget, we also have to take the 2/3 power of 8. People tend to forget that one. Here, unless the variable part has the same exponents, we're not going to be able to add them. Now looking ahead, I think they're going to become the same exponent. We'll be able to add them. So here, we're going to get 8 to the 2/3, and then x to the 1/2 to the 2/3. Let me get a better marker here. and then plus 9x to the 1/3. Now we should be able to do x to the 2/3, right? That's the cube root of, or I said x, it's 8 to the 2/3. So we know the cube root of 8 is 2, and 2 squared is 4. And this, when you multiply 1/2 times 2/3, you get 1/3. Right, so 4x to the 1/3 plus 9x to the 1/3. So we get 13x to the 1/3 is how I would write it. You could see it as a cube root, but we tend to, since we started with rational exponents, I want to leave it that way. Okay, next up from our paper, let's look at number 15, which is a compound or complex fraction. There's a whole lot going on. Probably hard to figure out what in the world you're going to do here. So I would think there's lots of ways to simplify this, but what I'm going to recommend is that here we notice that the radical x minus 2, and then there's an x minus 2 down here. Right? So that factor x minus 2 is a part of this. So what I would recommend you do in a problem like this is let's get the top to have a common denominator. Okay? And then we can use the fact, either like a copy change flip, multiply by the reciprocal thing, or just take a factor and move it to the denominator to kind of see what we're doing here. So first step is I want to get a common denominator, right, in the numerator. So I'm going to multiply this part of the numerator by radical x minus 2 over radical x minus 2. Is that good? It's just a form of 1. We can do that. We're not breaking any rules. So we're going to take the radical x minus 2 that's there and multiply it by radical x minus 2 over radical x minus 2 plus 5 radical x minus 2 over x minus 2. So all I did is I multiplied in by this factor here. Okay. Now when I multiply these two together, radical x minus 2 times radical x minus 2 is just x minus 2. So we'll do that. So x minus 2 over radical x minus 2 plus 5 over radical x minus 2 over x minus 2. So, now, up top we do have a common denominator, correct? So we can write this, it'll be x minus 2 plus 5. There's nothing touching this one. So we're going to get x plus 3 over radical x minus 2 over x minus 2, which I put it in a parenthesis because I'm looking ahead, but still an x minus 2. All right, now, but that is an x minus 2 to the first power, if it did have an exponent. So now at this point, it's better. Now we just have one fraction over an expression, but we just want to have one fraction, right? A numerator, a denominator. You don't want to have to say things like the denominator or the numerator, or things like that. That's not what we're going for here. So with this, what I would do here is I'm going to write this as x plus 3 over radical x minus 2 times 1 over x minus 2. So instead of dividing by x minus 2, I'm going to multiply by the reciprocal. Do this all the time when you're trying to get your fractions to look nice, right? Multiply by the reciprocal. So when we do this now, if you stopped and said x plus 3 over radical x minus 2, x minus 2, that's not wrong, but these are the same factor, correct? So as we go through that, we could leave the x plus 3 on top. That's not going to change. It's not going to cancel. But let's think of this as x minus 2 to the 1/2 power times x minus 2 to the first power.
Attention, please. Any students...
All right, does this look okay then? I rewrote the square root of x minus 2 as x minus 2 to the 1/2. Same base, add the exponents. So x plus 3 over x minus 2 to the 3/2. That's a terrible 3. Probably how you want to leave it that way. Right? Now, if for some reason you didn't want to have a denominator, which would be okay. And here, I know there's a radical in the denominator. I know there still is. as long as there's a variable, it's fine. It's not going to cause us any problems. But you do want to be aware this also could be written as x plus 3 times x minus 2 to the negative 3/2. There will be times where this would be useful to us, like more useful than this. So again, it's just about kind of knowing our rules and kind of working our way through those. Or maybe you would even, I don't feel like this is ever going to be very useful, but maybe that's useful too, right? So we have a lot of different options here. We just want to get used to manipulating things. Okay, 16, if you would write this using square roots, you'd have a square root of x minus 3 minus 3 over the square root of x minus 3 over x minus 3. So you could go back and do the number 15 we just did kind of using this technique, or you could go back and use the technique we just showed. They all work. That's the nice thing about algebra. If you follow the rules, you know, it might not be the quickest way, but it'll work. This looks like the answer to a quotient rule that we'll do later on. But what we have here in the numerator is you have two factors, or you have two terms, correct? You have this first term, which is x minus 3 to the 1/2 power. And then your second term, which is 3 times x minus 3 to the negative 1/2 power. They have a common factor of x minus 3, and we're going to factor out the lowest power of the numerator. So we're going to take out x minus 3 to the negative 1/2, and then we're going to take, whenever you factor, you divide the original, right, by that. So if you take this and divide it by x minus 3 to the negative 1/2, well, you have a base to a 1/2 over divided by a base to the negative 1/2. So when we subtract them, we just get the base, correct? So this is just going to be x minus 3. Oh, that's a plus though. X minus 3. And then minus 3, and then this comes out completely, doesn't it? The second factor gets divided out completely. And then don't forget about our denominator. Now over here, we could clean this up a bit, right? Just becomes x minus 6. Now at this point, this is not wrong, but you probably don't want the same factor twice. Can we move this factor to the bottom? Or could we subtract the exponents? You'd get negative 1/2 minus 1. However you do it, I kind of like to move it. So I'm going to say x minus 6 over x minus 3 to the 1/2 times x minus 3 to the first. Just remember that is a first power. We can go ahead and add those exponents. You get x minus 6 over x minus 3 to the 3/2. And of course, since these factors are completely different, we can't do anything with them. It's just good to know they're the same. Good. So again, this is pretty much the same thing we just did in 15, but it's got a different look to it. In order to study, I would recommend go back, write 15 and 16 on a separate sheet of paper. Make sure you can do them. Make sure you get the right answer. Okay, and it's kind of to wrap up today to get you so you could do the bottom of this worksheet on the front, is that we're going to just talk about how to rationalize the denominator, which is something you should have been doing for a long time if there's a number or something in the denominator. There's also times we're going to want to rationalize the numerator, which seems different, but it's really the same exact process. We just have to recall what it is. The first one I have here is 6 divided by the cube root of 5. Whenever you have a single radical in the denominator, just a single term, all we have to do is multiply with something to where we want to get the cube root of 5 cubed, right? Because we know the cube root of 5 cubed cancels out, becomes just 5. So we have 1 5 under the cube root. We need 2 more. So in this case, what we would do is do 6 times the cube root of 5 times the cube root of 5 squared, cube root 5 squared, which again looks like more of a mess than when we started. But what happens here is up top we get the 6th root of the cube root of 5 squared. I think there's a 25 on the way there. I don't really like writing down 5 squared, but we can do that. But on bottom we get the cube root of 5 cubed. Right? And we know that if you think back to our exponent rules, this is like 5 to the 3/3 power, which is just 5 to the first power, which is a rational number. So here we could write this answer, 6 times the cube root. I'm going to go ahead and put 25 in there, and then over 5. Again, I'm kind of leaving cube roots because we started with the cube root in the problem. Now this is equivalent to 25 to the 1/3 power, or you could say 5 to the 2/3 power, but probably want to leave it as a radical there. So if you have a single radical on bottom, just a single term, that's what you want to do. It's pretty straightforward. Now if we look at something like example 2, we would love to have the square root of x squared, wouldn't we? But if you multiply the numerator and denominator by the square root of x, I don't care what happens to the numerator, but that would become x, but this would become negative 3 radical x, which doesn't help. We got rid of one radical and replaced it with another. So what we have to use here is, hopefully you remember, it's called the conjugate. Okay, the conjugate. So a plus b and a minus b are called conjugates. The reason they get a special name is that if you do a plus b times a minus b, you just get a squared minus b squared. You're forming a difference of two squares pattern. Now, the reason we want to try this here, for example 2, is that we need this to get squared. If you square a radical x, it just becomes an x, right? And I'm fine if we just square a 3. That's not a big deal at all. But if you don't know to use the conjugate, you'll never figure it out. Like you'll get one fixed and the other one will get a radical in it. You just keep chasing it like whack-a-mole. Radicals. So let's take 2x times radical x plus 3. Again, the conjugates, same two terms. One has a plus, one has a minus. And then on bottom here, we have radical x minus 3, radical x plus 3. I'm up here in the numerator. We could probably leave it like it is, maybe. Or we could try to simplify it later, but it's really not bad. It's factored. I mean, not bad. So 2x, radical x plus 3. Then on bottom, when you go ahead and multiply, you don't need to multiply it out because it just fits the special pattern. But if you did, you get x squared plus 3 radical x minus 3 radical x minus 9. So once we do that, on bottom we get x minus 9. And we rationalize the denominator. Right? X and 9 are rational numbers. The radical x was not. But if you have two terms, you have to use the conjugate. All right, so here, for example 3, it's already a rationalized denominator. Okay, now this is the type of thing we'll see when we start doing limits. Sometimes you want to rationalize the numerator. For now, you would be told rationalize the numerator. On this worksheet, if the numerator's a mess, rationalize it. If the denominator is, rationalize it. But we'll look more in the future when we would do this. But here what we'll do, so we have radical x plus 2, and then x minus 4, and we're going to multiply by radical x minus 2, radical x minus 2, on top and bottom. Now, on bottom, we just have two factors. I don't multiply them together. Really only tend to multiply factors if there's a reason. But here I do want to multiply up top because we see we have our difference of two squares pattern. So we're going to get x minus 4 on top. Then we have x minus 4 over radical x minus 2 on bottom. Well, we have a factor on top and bottom that'll cancel. So we get 1 over radical x minus 2. Later when we do limits and things, or the definition of derivative, this works for us where this does not work for us. Possibly. Or maybe I should have used a different symbol. But anyways, it's good. It's fine. We can make it work. But you see now, here there was an irrational number, the radical in the numerator. There no longer is. Now it's in the denominator. That's what it means to rationalize.